But what if you have a frequency distribution? So if we have a frequency distribution, what we're going to do is we're going to use the midpoint for each class to represent the data values in that class, right? So if you think back to what our frequency distributions looked like in the last chapter, right? So whenever we built that frequency distribution, we lost our raw data and we put it into these groups, right? So we don't have any, if we just have the frequency table, right? We don't have any way of knowing what those individual data values in each of these classes are, right? And so instead, what we're going to do is we're going to use the midpoint to represent a typical value, because if you think about how we get that midpoint, right, we're adding up the two limits and dividing by 2, right? So that midpoint is going to represent the middle of that class. So, and remember, middle means a typical value. So we're going to use midpoints to represent the data values within each class. So then what we're going to do basically is we're going to say, okay, we're going to use that midpoint and add it up however many times we're counting in that class, right? But what is repeated addition? It's multiplication, right? Repeated addition is nothing but multiplication. So whenever we look at our mean formula, it looks slightly different, right? So if we have a frequency distribution, it looks slightly different. Now keep in mind, this is going to be an approximation, right? Just because we're not actually working with the raw data values. We're working with class midpoints. So our sample mean, it's going to be the sum of the midpoints for each class times the frequency for each class. So that's representing that multiplication there is representing that repeated addition, right? Of adding that midpoint plus that midpoint plus that midpoint, however many data values we have in that class, divided by our sample size or population size of n, right? So n, remember, is just the sum of our frequencies. So it looks a little bit different, but it's really the exact same math. And so this slide just kind of walks you through the step-by-step process, right? So you would find your midpoints, which we're doing as part of that frequency table anyways, right? And then find the sum of the products of the midpoints and frequencies, sum of the frequencies, and the mean of the frequency distribution. So we'll come back and look at a full example walking all the way through this whenever we get into standard deviations. But basically, I would give you a table, just like I would for weighted average. And really, you can think of this as a weighted average, right? Where your frequencies are your weights. That's really what it is, right? So if you think about our weighted average formula from yesterday, right? The weighted mean or the weighted average. It was the sum of the data values times the weights divided by the sum of the weights, right? So if I replace that weight with frequency, right, you get, it's the sum of the data values, which is our midpoints, right, times the frequency divided by the sum of the frequencies, right? So that is the sum of x times f divided by n. So it is the same thing. It's a weighted average. It just looks a little bit different, and we're really doing the same math. All right, so here I've got a frequency distribution that's showing the out-of-pocket prescription medicine expenses for 30 U.S. adults in a recent year. And so we want to use this distribution to estimate the mean expense, right? So I helped you out a little bit. I gave you the midpoints already. I gave you the frequencies already. And we did the data values time, or the midpoints times our frequencies, and added them up for you. So really, it's just plugging into that formula, right? So x bar is going to be approximately the sum of x times f divided by n, right? So really, in this case, it's going to be the sum of this last column, the 8631, divided by 30, right? We're going to get 287.70, right? So if you had the raw data, which you don't have here, but if you had the raw data, you'd find out that the actual sample mean of this data set was 285.50, right? So notice we're not very far off using those midpoints. So it's still going to be a decent enough approximation of the middle if you don't have the raw data. Something we're going to get off of this is the shape of our distributions, right? So if we have symmetric distributions, and this is going to be what most distributions we're going to talk about in this class are going to have. Because most things in the real world take on a symmetric distribution or something close enough to a symmetric distribution. So a symmetric distribution just means it kind of has that mirror image on either side of it. So if you draw a line down the middle, you've got a picture that looks the same on both sides. So your data values kind of go out evenly away from that middle. So with a symmetric distribution, your mean, your median, and your mode are all going to be around the same spot, right? So kind of a visual look at it. So kind of going back to those histograms, right? So if you can look at your histogram and see your data set looks like this, it has what we call typically a bell-shaped distribution. So you're going to see me draw that picture a lot this semester, a bell shape. So if it has a symmetric distribution or a bell-shaped distribution, then your mean, median, and mode are all going to be pretty good guesses at the middle, right? They're all good representatives, but we're still going to typically use mean where we can. All right. A uniform distribution is a special symmetric distribution, right? So it's still going to be symmetric. If I draw that line down the middle, I still have that mirror image on both sides, right? But the difference is that every single data value or every single class has the same frequency. So in other words, there's not going to be a mode. It's just a flat box distribution. So our middle still represents the mean and median, but because everything is flat, there is no one class that stands out above everything else, right? So we don't have a mode in this case. It's worth mentioning, symmetric distributions are typically going to be unimodal, so one mode. All right, the third type of distribution, and really third and fourth, are skewed distributions. So we have a skewed left distribution or a negatively skewed distribution. That's just so kind of going back to yesterday with the outliers, right, and that sumo wrestler. So that's where our sumo wrestler is pulling to one side or the other side. So whichever side your quote unquote sumo wrestler is standing on, that's the direction of the skew. So in this case, the skew is on the left-hand side. So most of your data values are all over here, but it's being pulled this way by your tail or your outliers. Now, in this case, we wouldn't really call this an outlier, but we would say it has that kind of elongated tail. So if I kind of trace around this to give you the rough shape, right, then it's going to kind of everything's going to kind of trail off to one side on the left-hand side, but away from the bulk of the data. So the skewedness follows the direction of the tail. But notice what that does to our measures of center, right? So because we have these lower data values over here kind of pulling things that way, right? You got that sumo wrestler on the end of your rope. Well, he's pulling that mean more to the left. Your median's still going to be right around the middle data value, but it's going to be slightly more to the left than it would be if it weren't skewed. Your mode's not affected, right? Your mode's still the peak. Similarly, in a skewed right distribution, it's the opposite case, right? So now that sumo wrestler is over here on the right-hand side. So it's just pulling to the right instead of the left. But same idea. So we call this one skewed to the right or a positively skewed skewed in the positive direction. But same thing, it's going to pull that mean more to the right in this case than it would be otherwise because of those higher data values.